Now we are ready to define some modes of convergences. So in this chapter, we defined several modes of convergence, but there are other different modes of convergences that you can define or use if you need them, and you will learn about that. So modes of convergence of a random sequence is not unique, and we'll present some of them, the important ones. The important ones are, the first one is convergence everywhere. This mode of convergence is deterministic, and it is that for all possible outcomes of your random experiment, you consider, you specify the value of your outcome, and you consider these sequences. If all these sequences for different possible outcomes, they converge to certain real number, then we say convergence everywhere. So this is the ultimate convergence mode of convergence everywhere for all possible these. So this notation means for all. So for all possible outcomes, if the sequence is converging, we say, but this definition is too broad, too strong, and is quite often useless in the case of a stochastic. So if you could do that, you don't need a random process. You don't need to learn this course. We learn this course because this convergence doesn't happen often. So this convergence is too strong, it's deterministic convergence, and it shall happen regardless of randomness. The second type of convergence is much weaker than the previous one, is almost everywhere. So we say that a random sequence converges to X, to a random variable. This is a random variable. This is a random sequence. We say that this random sequence converges. We denote it by that. So we put arrow here, and we say that A point, E point means almost everywhere. Sometimes in literature people say almost surely, or convergence with probability 1. So we see why we call it. So we say a random sequence converges to these if there exists a subset of all your possible outcomes such that probability of this event A is equal 1. So that means that the support of probability of A outside of A is 0. And for all possible outcomes inside A, you have this convergence. In other words, for those points that x of n doesn't happen, you may have not convergence, but for those points that probability is non-zero, you have this convergence. If you have this first type of convergence, automatically this type of convergence is implied, but not the other way around. So we'll have some examples. Another type of convergence, which is almost everywhere, this type of convergence, sometimes we refer it almost surely or with probability 1, is a stochastic convergence. And this type of convergence depends on your probability measure. But the first one, you see that probability doesn't appear, but here probability appears. So this is a stochastic convergence. This is not a stochastic convergence. So this is a big difference. Another useful mode of convergence is that we consider the difference between x of n and x is mean squared error. So if this is, because this becomes real, as soon as you put expectation on some random entities, this becomes real. So this becomes a sequence. If this sequence tends to 0 as n goes to infinity, then we say that x of n converges to x in mean square sense. So this is a notation. This notation means this definition. So these two are equivalent. So this is an abbreviation. So this notation is abbreviation for this sentence, and it means this mathematical definition. So convergence in mean square sense is heavily used in estimation in lots of applications. Obviously, instead of mean square, if you remove this squared here and you put just instead of 2 you put 1, it is called convergence in L1 or L1 norm. So convergence in L1 or L1 norm. So there is a relationship between these two. So one of them is stronger than the other one, and we have to learn which one is stronger. Similarly, you could have convergence in like L to the power. So if you say x of n minus x to the power of p, expected value of that, if limit of these when n goes to infinity, if this is equal to 0, this sentence means to say that x of n converges to x in LP norm. And p could be 1, 2, 3, or it could be even infinity, or sometimes p could be even 1/2. So p could be 1, 2, etc., or p could be 1/2, or sometimes p could be infinity. We call it L infinity norms. So this is one class of convergences which are defined by norms and so on. There is another type of convergence, we call it convergence in probability. Remember that, don't confuse yourself this one with convergence with probability 1. Convergence with probability 1 was something else that we defined on the previous slide. This convergence in probability means that if the distance between xn and x, because this is a random variable, if probability that this random variable is bigger than epsilon, if this probability reduces to 0 as n goes to infinity, if this probability reduces to 0 as limit of this when n goes to infinity, for all epsilon, okay, all epsilon which are positive, then we say that x of n converges in probability to x. That means that in probability, the distance between xn and x cannot be large for any small number, for all arbitrary non-negative numbers. You could reduce this distance in terms of probability to 0. And the last definition that we define here is the convergence in law. Obviously, we'll talk about other convergences, but these are the more important one. If you learn these important one, other ones are going to be very easy. So we say that a random sequence converges to x in distribution if its distribution converges to x. So this definition means that let's say the CDF of xn be denoted by that, and CDF of x be denoted by that. So this definition means that the CDF of x of n, whatever it is, limit of that CDF of x of n when n is large enough becomes a constant function, becomes a constant CDF. If the CDF of your distribution when n is large enough becomes constant, or if the CDF settles down somewhere. So we call it convergence in distribution or convergence in law. Sometimes we put in law or convergence in distribution, or simply d dot. So these are the main modes of convergence. Of course, if the distribution of a random sequence becomes constant, obviously its mean also becomes constant. For instance, if you have convergence, if x of n converges to x in distribution, you can say, oh, mean of x of n should be equal to mean of x when limit of n goes to infinity. So you have convergence in mean sense as well. If you have convergence in the sense of law or in the sense of distribution, convergence in the sense of mean or in the sense of variance and so on becomes obvious. So this convergence is stronger than convergence in the mean sense or variance. But other previous modes of convergences are stronger than this one, and we'll see that in the next